Welcome, Math 13 students. I have my office hour lecture for the Goodness of Fit test. This is section 11.1. And we're going to encounter a couple of new things in this particular section. We're going to broaden our definitions or our use of distributions and introduce a brand new distribution that we have not used up until this point. And what we're going to work on here is what we call the goodness of fit or good fit test. And this is used to test the hypothesis that an observed frequency distribution fits some sort of claimed frequency distribution. It's very much like a binomial distribution type of question. The only thing is you've got more than two outcomes. So you might have 3, 4, 5, 6 different possible outcomes, maybe even more. So it kind of broadens that general notion. It's what we refer to as a multinomial data set. So it's not binomial, it's multinomial. So let me give you a quick example, and then we'll get into the detail. Because as I say, this is a new situation. We've got some new notation and a new distribution to look at. So here's a simple question. Are workers absent with equal frequency during the week? So you've been around the block a few times. Do you think workers are more likely to call in sick on, say, a Monday or possibly a Friday, or perhaps more likely to call in sick in the middle of the week, or perhaps they call in with pretty much equal frequency no matter what the day of the week is? Just depends if they're feeling ill or not. So I have an observation. We went out, we gathered a sample in a particular business. 14 people were absent on Monday, 7 on Tuesday, 8 on Wednesday, 8 on Thursday, and 23 on Friday. That's my observed sample. Now, the question that I posed is the question of absence with equal frequency during the week. That just means that people are absent about the same number of times Monday through Friday. No one day is, if you will, preferred. Now, to actually figure out what would be expected with equal frequency, we need a total. And if I add up, type in here, I'll fix it as we go. If I add up my observations, I had a total of 60 observations, 14 plus 7 plus 8 plus 8 plus 23. And if those absences were to be distributed evenly with equal frequency throughout the week, there's 5 days in the week, so I would expect 60 divided by 5, or about 12 absences per day for my employees. So my expected values, 12 people missing every day of the week, 5 days out of the week. That's my expected frequency. At least that's what it is when we have the claim of, as I noted, equal frequency. Now, before I go any further, I need to introduce some notation. The letter O, capital O, is going to stand for observed frequencies. Those were the 14, the 7, the 8, and the so on and so forth. The letter E, big E, is going to stand for the expected frequencies. Now, in my case, with the claim of equal frequencies, they were all the same. We'll use the letter K to give us the number of categories. So in that particular example that we just got done looking at, there were 5 categories because there were 5 days out of the week. N was the total number of observations. In fact, I'm going to put that in there. For that example that we just looked at, K was equal to 5 and N was equal to 60. And then the probability that a value falls within a particular category, my expected probability, well, let's see, there were 12 observations out of a total of 60 or 1/5 or 0.2. That would be the probability that someone would fall into any one of those categories there. So there are requirements here. We want a random sample, simple or better. We need frequency counts by category. This requirement just ensures that we've got the right kind of data for this kind of test. And we need the expected frequency to be greater than or equal to 5 for each of the categories in question. For our example, it was n equals 12, or excuse me, e equals 12. So we were we were well positioned there. Now, the distribution that we use is a different distribution. It's not a normal distribution at all. It's something else. We use something called the chi-square distribution. Chi-square, that's not an X, it's a Greek letter, capital Greek letter. And even though it looks like it says chi, it's pronounced chi. Rhymes with sky, y, and try. Chi. So the chi distribution has a degree of freedom. In this particular case, that's the number of categories -1, not the number of observations, not n-1, but the number of categories -1. Now, before I go any further, because this is a new distribution, I feel I should say a little bit about this. It's a probability distribution, very much like the Z or the T distribution. But it starts here at 0, and it only exists from there to the positive side. It doesn't cross the y-axis. The total area under that graph is equal to 1, just as it is for any probability distribution. There is a critical value if we want to use a traditional method. And because of the nature of the test, for large chi-square values, and this is really the nuts and bolts of it, for large chi-square values, we reject our null hypothesis. So that means my test statistic would fall in the rejection region. If the chi-square value is small, on the other hand, we fail to reject that null hypothesis and we'll keep it. It's important to realize this means all our tests are right-tailed tests. All of them are right-tailed tests. Now, I've included our test statistic. This one, believe it or not, is actually fairly easy to calculate by hand. The critical value is a little bit more complicated to come by because it's a new distribution, but that's okay. Our calculator is going to make short work of this, and it really does a bang-up job on the chi-square distribution problems. One of the reasons this is set up is actually a bit easier. There's no, like, what tail of the test do we deal with? They're all right-tailed tests. We just want to make sure something is larger than we would expect. If the value, the fraction, if you will, is larger than we expect, then we get to reject the null hypothesis. That also means that our claims are somewhat different. The null hypothesis is, the claims are that the frequencies agree with the claim distribution. The alternative hypothesis is they do not agree with the claimed distribution. We have a dedicated tool called the chi-squared goodness of fit test. No, it's not golf. Goodness of fit. I need to include my observed values, and I'll put those observed values in list number 1. I need expected values, and I'll put those in list number 2. Now, the only thing that slows a student or an instructor down in doing one of these problems is to forget one important thing. For the expected values, we need to find n. Once we know n, then for equal frequency, so if that's our claim, the claim of equal frequency, the expected number of observations for each category would be n divided by k. The problem we looked at, we had 60 divided by 5 or 12. So that was the one that we looked at earlier. But to get to that 12, I had to know the 60, which means I needed to know the sample size. The total number of observations. And that's the one little bit of work that needs to be done prior to conducting the test. So let me go through the example. We'll see how it goes. We have the claim of absence with equal frequency. That means the probability of being absent on Monday is the same as on Tuesday, all the way through Friday. There's my data set. There's my expected values. So let me jump over to my calculator, and we're going to run through the test of the claim. And we're going to use a 1% level of significance. Maybe I'm a boss and I'm mad at my workers. Maybe I'm a union and I want to justify higher wages because we work so hard. So we're going to test that claim. Let me switch to Mr. Calculator. There you are. Come here. Thank you. So the first thing I need to do, as I say, is to go ahead and add my observations up and make sure I've got 60 observations. So I am now ready to go ahead and plug in my data. Under Stat, in Edit, I've got my observations, my 14, 7, 8, 8, and 23, number of absences from my employees. Now over here, I am going to plug in, I can plug in the number 12, but I tell you what, it's not always a simple fraction. So I'll type in literally 60 divided by 5, 60 divided by 5, 60 divided by 5. Believe me, the ones you see on your quizzes and on your exams are not simple whole numbers. So you'll be wanting to round. You'll no doubt make some sort of error. Most students do with that. Not an error of rounding, but an error of how much to take. So don't let yourself get stuck with that. Let the calculator do the arithmetic for you. Now, let me jump back over here for just a moment. All right, so I will note that the null hypothesis is that the employees are absent with equal frequency for the days of the week. And the alternative hypothesis is that the absence rates are not equal. There's a couple of different ways you might set this up, but this is really the most straightforward. I am now ready to go ahead and find my p-value. As I say, it's a very easy test to do. It's late in the semester, so the tools are down near the bottom now. There it is, chi-square goodness of fit test, not golf. And that's not an X, that's a chi-square. Don't confuse it with the one right up above it. We'll be looking at that in the next section. Notice I've got a place for my observed and a place for my expected in terms of lists. I've already prepared my lists. So list 1 and list 2. The degrees of freedom, 5 minus 1. The number of categories minus 1. I'll sit there and hit calculate, and there we go. 0.00437 with rounding. Let me stop my sharing. 0.00437. So 0.00437, 0.01, because we have a 1% level of significance. My p-value is less than the level of significance, so we will go ahead and reject H naught. So at alpha equals 1%, data do not support equal frequencies. Bottom line, some days have more absent employees than others. Probably not that big of a surprise. 1, 2, 3, 4, 5, 5.5. So those are the details that one needs to work with when one works with a goodness of fit test. So I'm going to go ahead and end my office hour lecture and point out that there are more videos in our Canvas course shell. Please shoot me any questions regarding the test for goodness of fit. There is some detail if the probabilities, or excuse me, the frequencies are not expected to be equal, but I'll let you read about those and see what you think. Anyway, you all be well, and we'll see you soon. Bye-bye.